So, for today, we'll be discussing about the main type of methodologies in the assessment of the desirability in economic and environmental or social aspects of constructing a highway proposal.
Once a transportation plan has been finalized and the demand along each of its highway links has been established, a process must be put in place that helps identify the best solution for each individual proposal within the highway network. Each project must therefore be subject to an appraisal. The aim of the highway appraisal process is therefore to determine the economic, societal, and environmental feasibility of the project or group of projects under examination. The process enables highway planners to decide whether a project is desirable in absolute terms and also provides a means of choosing between different competing project options, all of which have the ability to meet the stated goals and objectives of the project sponsors. The reasoned choice model of individual or group decisions provide a decision-making framework within which scheme appraisal can take place, providing a technical foundation for non-recurring decisions such as the assessment of a highway construction or improvement proposal. So, this comprises of the following steps. The first one is problem recognition. So on this step, the decision maker determines a problem exists and a decision must be reflected on. The second one is goal or identification. The decision maker details the desired result or outcome of the process. Next is identification of alternative highway schemes. So different potential solutions are established or assembled prior to the evaluation. Next is information search. So the decision maker seeks to identify characteristics associated with the alternative solutions. Next is assessment of information on alternative highway schemes. On this, the information necessary for making a decision regarding the preferred option is gathered together and considered. Next one is selection of preferred highway scheme. So after assessing, a scheme will be selected. So a preferred option is selected by the decision maker for implementation in the future. And also, the last one is the evaluation. The decision is assessed a period of time after its implementation in order to evaluate it on the basis of its achieved results. So clearly, rationality, where judgment is arrived at the following sequence of deliberately followed logical steps, lies at the basis of this model for decision making. The principle of reasoned choice has been adapted into an analytic technique called the rational approach. So the scheme appraisal process for highway schemes can broke down broadly in two sections: economic evaluation and environmental assessment.
Next is we have economic appraisal of highways scheme. The developer will require economic assessment of the route options under considerations. This will involve comparing their performance against the current situation termed the do-nothing alternative against the do-minimum alternative, involving a low-cost upgrading of the existing facilities. Computations are performed on the cost and benefits associated with each highway option in order to obtain one or more measures of worth for each. Engineering economics provide a number of techniques that result in the numerical values termed measure of economic worth. So some common measures of worth are net present value, benefit cost ratio, and internal rate of return.
In economic analysis, financial units such as pounds, euros, and dollars are used as the tangible basis of evaluation. So, with each of the measures of worth stated, the fact that a quantity of money today is worth a different amount in the future is central of the evaluation. So, next one is the cost-benefit analysis. On cost-benefit analysis, this utilizes the net present value technique where the cost and benefit of the scheme are discounted over time so that they represent present-day values. Using this method, any proposal having a positive net present value is economically sustainable in absolute terms.
Under the cost-benefit analysis, we have identification of the main project options. This is a fundamental step in the cost-benefit analysis process where the decision makers compile a list of all relevant feasible options that they wish to be assessed. It is useful to include a do-nothing options within the analysis in order to gauge those evaluated against the baseline scenario where no work is carried out. The do-minimum option offers a more realistic course of action where no new highway is constructed but a set of traffic management improvements are made to the existing route in order to improve the overall traffic performance. Evaluation of the do-nothing scenario does, however, ensure that in addition to the various live options being compared in relative terms, these are also seen to be economically justified in absolute terms. So in other words, their benefit exceed their cost. The term feasible refers to the option that, on a preliminary evaluation, present themselves as viable courses of action that can be brought to a conclusion given the constraints imposed on the decision makers such as lack of time, information, and resources. So, there are many procedures for both identifying and defining options. Here are some procedures. The first one is drawing on the personal experience of the decision maker himself as well as the other experts in the highway engineering field. The next one, making comparisons between the current decision problem and ones previously solved in a successful manner. And the last one, examining all relevant literature. Next to identification of main project option is identification of all relevant cost and benefits. The application of cost-benefit for project assessment in a highway area is made more complicated by the wide array of benefits associated with a given road initiative, some easier to translate into monetary values than others. The primary grouping that contains this type of economic gain is termed user benefits. Benefits of this type accrue to those who will actively use the proposed installation. So this grouping includes reduction in vehicle operation cost, saving in time, and reduction in the frequency of accidents. After the identification of all relevant costs and benefits, we have economic life, residual value, and the discount rate. A highway project is often complex and long-term, with the cost and benefits associated with it occurring over a long time frame, which we term the life of the project. It sets a limit on the period over which the cost and benefits are estimated, as all must occur within this time slot, like 25, 35, or over 50 years and more. It is related in principle to the expected lifetime of the project under analysis. So given that transport development projects have the potential to be in service for a very long time, it may seem impossible to set a limit of the life of the projects with any degree of certainty. However, this may not give rise to serious problems in the evaluation, as the loss of accuracy that results from the limiting the life of the project to 35 to 40 years. The difficulty in assigning a meaningful residual value to a project after so many years in the commission results in this solution being rather unsatisfactory. So the discount rate, which translates all cost and benefits to the time equivalent values. The actual value used is the social discount rate, given that the decision maker is interested in the benefits and cost to society as a whole rather to any individual or group of individuals. The next one is the use of economic indicators to access basic economic viability. This, the decision maker must know, choose the actual mechanism for comparing and analyzing the cost and benefits in order to arrive at the final answer for the net benefit of each of the product options under consideration. So any of the three techniques such as can be used for this purpose, so such as net present value, internal rate of return, and benefit cost ratio. So on the net present value, it will estimate the economic worth of the project in terms of the present worth of the total net benefits. The internal rate of return will give for each option under the consideration the rate at which the net present value for it equals 0, with the benefit cost ratio based on the ratio of the present value of the benefits to the present value of the cost. So all the three methods depend on discounting to arrive at the final answer. So all, if used correctly, should give answers entirely consistent with each other. But if the same specific technique to be used varies with the circumstances, so selecting a criterion for deciding between project options can be consensus. Some decision makers are used to incorporating certain techniques in their analysis and are loath to change.
Next, we'll be discussing about the advantages and disadvantages of cost-benefit analysis. The final output from a cost-benefit analysis, according to Kelso, should be a cardinal number representing the dollar rate of the streams of net prime benefits of the proposal that he termed pure benefits. Pure benefits measured the net benefits with a project in relation to the net benefits without the project. So another one, Hill believed that this statement, one that explicitly sets out the basics for a traditional cost-benefit analysis, reveals some of the major deficiencies in the technique. Although there are some considerations of the intangibles, they tend not to enter fully in the analysis. So as a result, the effect of those investments can be measured in monetary terms. Here are the disadvantages of cost-benefit analysis. The first one is the primary basis for constructing a highway project may be societal or environmental rather than economic one. If the decision is based solely on economic factors, however, an incorrect decision may result from the confusion of the original primary purpose of the proposed project with its secondary consequences, simply because the less important secondary consequences are measurable in money terms. So the second one is the method is more suitable for comparing highway proposal designed to meet a given transport objective rather than evaluating the absolute desirability of one project in isolation. This is partly because all estimates of cost and benefits are subject to errors of forecasting. A decision maker will feel more comfortable using it to rank a number of alternative highway design options rather than to assess the absolute desirability of only one option relative to the existing do-nothing situation, though this in some cases may be the only selection open for the decision maker. So lastly, we have payback analysis. It is an extremely simple procedure that is particularly useful in evaluating proposals such as privately funded highway projects where tolls will be imposed on users of the facility in order to recover construction costs. The method delivers an estimate of the length of time taken for the project to recoup its construction cost. It doesn't require information on an appropriate interest rate, but the lack of accuracy of the method requires that results from it should not be given the same weight as those from formal economic techniques outlined. Such as cost-benefit analysis. This method assumes that a given proposal will generate a stream of monies during its economic life, and at some point, the total value of this stream will exactly equal to its initial cost. The time taken for this equalization to occur is called the payback period. It is more usefully applied to projects where the time scale for equalization is relatively short. The method itself does not address the performance of the proposal after the payback period, Its analysis is thus not as complete as the more formal techniques, and therefore its result when taken in isolation may be misleading. It is therefore best utilized as backup technique, supplementing the information from one of the more comprehensive economic evaluation methods. So its strength lies in its simplicity and basic logic. It addresses a question that is very important to the developer of a tolled highway facility, as a relatively speedy payback will protect liquidity and release funds more quickly for investment in other ventures. Highway projects with a relatively short payback period can be attractive to a prospective developer. The short time frame is seen as lessening the risk associated with a venture, though road projects are seen as relatively low-risk enterprises. So we have the equation. Payback period denoted as N sub P is equal to C sub O, which is the initial construction cost of the highway projects divided by the net annual savings. So, on the equation, it assumes that a zero discount is being used. This is not always the case if it is assumed that the net cash flows will be identical from year to year and that these cash flows will be discounted to present values using a value of I such that it is not equal to 0, then the uniform series present worth factor P over A can be utilized within the following equation. So, the initial construction cost plus the net annual savings multiplied by the present worth factor. So, to obtain the correct value of the payback period, this equation is solved to obtain the correct value of N sub P. The method is, however, widely used in its simplified form with the discount rate I set equal to 0, even though its final value may lead to incorrect judgments being made. So if the discount rate I is set equal to 0, so the equation is obtained. The initial construction cost of the project plus the summation of the net annual income with respect to its discount rate, considering the discount rate. So we have an example of the comparison of toll bridge project based on payback analysis. So here's the problem. A developer is faced with a choice between two development alternatives for a toll bridge project. One large-scale proposal with higher cost but enabling more traffic to access it, and the other less costly but with a smaller traffic capacity. So the details are of the cost and revenues associated are both given in there's a table. So we are tasked to calculate the payback period and check the result against the net present value. So on the table, there are two options. There option A and option B. So applying the equation, solving for the payback period. So for option A, so the initial construction cost divided by the annual profit, so this will have a 5.4 years. So as well as the by substituting on the option B naman, so 50 for the initial cost and 8 for the annual profit, we have 6.25 years. So on the basis of simple payback, the cheaper option A is preferred to option B on the basis that initial outlay is recouped in nearly 1 year less. So on the present worth, the formula that converts the annualized figure into present worth value, so termed as present worth factor, P over A. So we have the equation. So assuming as the discount rate is 0.08 and the years end is 20. So substituting on the equation, we have 9,818. So therefore, substituting on the equation to solve the present worth on option A, we have negative 27 plus 5 multiplied by the present worth factor. So we have 22.09. While on the option B, negative 50 plus 10 multiplied by 9.818, we have 48.18. So on the basis of its present worth valuation, option B is preferred, having a net present value over twice that of option A. So the result of option B is twice sa result ng option A. Thus, while payback is a useful preliminary tool, primary methods of economic evaluation such as net present value or internal rate of return should be used for the more detailed analysis.